Yeah, thank you, Elizabeth. So I'd like to thank the organizer for the invitation. So this is a joint work with Konstantin Tikhomirov, and I'm going to talk about outliers in sparse Wigner matrices. So let me set up, make the setting first, just to introduce the object. So if you are given a psi, a random variable, so which is centered, say, and has variance 1. What you care about in random matrices is that one of the most basic models is that you just take a symmetric matrix, which you populate by independent copies of this random variable. So you take psi ij here. So for psi ij, they all have the same law, which is this law of psi. So I'm going to always take the dimension of the matrix to be n. I'm going to call this matrix Wn, because that's what we refer to as Wigner matrix. And I'm going to just normalize, by, let me just remove this one. Normalize by 1 over root n, so that each Euclidean norm of the row is of order 1 on average. So this Wn is symmetric. And one of the most basic questions is how does the spectrum of this matrix look like? So how would we study the spectrum? We associate to this random matrix a random measure, which is called the spectral distribution. So what you do is you just define a measure mu Wn as being just the counting measure on eigenvalues. So you take the sum of the Diracs at the eigenvalues of Wn, and you just take the average. So what this measure does is just counts the proportion of eigenvalues which land in a particular interval. So mu Wn of some interval I is just equal to the proportion of eigenvalues which land into I. And one of the most basic, the starting theorems in the theory of random matrices is Wigner's semicircle theorem, which tells you exactly how does this measure behave. So Wigner semicircle theorem tells you that if you look at this measure, it's a random measure, so almost surely this measure converges to a deterministic measure, which we call the semicircular distribution. How does it look like? It's a measure which has density, which is the semicircle. So -2, 2, semicircle looks like this. So the density is f of x equals 1 over 2 pi square root of 4 minus x squared on -2, 2. Okay, so this measure tells me how the spectrum looks on a macroscopic level, like how does it look as a whole. So what the theorem tells us is that kind of most of the eigenvalues of Wn, they live in -2, 2. However, it doesn't tell you what happens to the extreme eigenvalue. It may be that there is a small proportion of eigenvalue which are like living outside of this interval and going away from the interval -2, 2. So what we're going to ask is, what about extreme eigenvalues? So in particular, what about the norm, basically? Does it stick to the bulk of the support? So does it stay glued to -2, 2, or is it like getting away? So whenever it goes away from the support, we're going to say there is an outlier. And whenever it sticks to the bulk, it means there is no outlier. Okay. So obviously this extreme eigenvalue cannot shrink below 2, right? Because otherwise the support of the limiting measure will be smaller. So 2 is the best we could. So we have an answer on this. So this is very classical. So there is results of German, I don't know how to pronounce it, and Bayin, which says that if your original random variable has moment of order 4, finite fourth moment, then there are no outliers. So then the norm of Wn is basically sticks to the bulk, so it's smaller than say 2 plus some O of 1 with high probability. So what I mean by this is there are no outliers. Now you can start asking yourself, how stable is this result? So what if we just start perturbing our random matrix Wn? What happens to this phenomenon? So let's say perturbation of Wn. So one of the most studied thing is you add some finite rank perturbation to your matrix. So you start with Wn. Say Wn is a very nice matrix. It has moments of order 4, so it doesn't have outliers. What happens if I add let's just as a basic example, take a rank 1 matrix. So I take X transpose, a rank 1 matrix. This is deterministic. Rank 1. So we asked what happens to the limiting distribution, what happens to the extreme eigenvalues. Now, for the limiting distribution, remember, you're just looking at the eigenvalues as a whole, just on a macroscopic level. You're looking at all of them. If you have a matrix and you add a rank 1 matrix to it, the eigenvalues interlace. So there is an interlacement of eigenvalues. So on a macroscopic level, nothing changes, basically. They look kind of the same. You may have pushed one, the extreme one, the biggest one, you may have pushed it further, but the others are interlaced, so they kind of stay the same. So the limiting distribution is just the same. So it is the semicircle. So, but what happens to the extreme eigenvalue? It may happen that this rank 1 matrix just was maybe pushing in the same direction as the largest eigenvector, so which resulted into pushing the largest eigenvalue very, very far from the bulk of the spectrum. And this phenomenon is well understood, and it's known as the BBP phase transition. So it's due to Baik, Benarus, Péchet. Maybe not in this form, but this is usually the phenomena is referred to as the BBP phase transition, which completely characterizes this. It tells you that if your rank 1 matrix is large enough, then you will start seeing outliers, and if it's not large enough, then you don't see anything. So if, let's say, so the rank 1 matrix, it's a rank 1 matrix, its norm is just equal to the Euclidean norm of the vector. So if the norm of X is smaller than 1, then nothing happens, so no outliers. So the largest eigenvalue is still smaller than 2 plus epsilon. And if norm of X bigger than 1, then you start seeing something. Then there exists an outlier. And it's given by, norm of X plus 1 over norm of X. Now this quantity norm of X plus 1 over norm of X is bigger than 2. So you get detached from the bulk, and you know how much you got detached, you are equal to this norm of X plus 1 over norm of X. Now in the literature, there are much more general perturbation, not necessarily rank 1. I mean, you have a lot of things. And maybe one interesting thing here is that, I mean, this question here has a lot of application, because you can interpret this guy here as a signal, and the random matrix plays the role of a noise. And you ask the question is how strong your signal should be in order to see it. How strong signal has to be. Kind of, I mean, maybe not to be lost in the noise, okay? Because if it is like, if you cannot see it, if you cannot see the eigenvalue corresponding to this one inside the eigenvalues of the other, so it's just lost in the noise. To be not lost in the noise. And the BBP phase transition tells you exactly how strong it should be. It has to be bigger than 1 in order for you to start seeing it. Okay. Otherwise, you just cannot see. Okay, so what we're gonna do in this talk, we're gonna also look at perturbation of this. So in this talk, so we're gonna perturb Wn by sparsifying it, okay, by sparsification. So what I mean by this is that I'm gonna take my matrix Wn, the one I had at the beginning, which had psi ij as entries, and I'm gonna just, for each coordinate, for each entry in this matrix, I'm gonna flip a coin and decide if I zero it out or not. So I'm gonna multiply basically all the entries by some Bernoulli variables. So Bij is just a Bernoulli. I mean, everything, all entries are independent in all of what I'm saying. So Bernoulli variable with parameter Pn. So P is allowed to depend on N. And I'm gonna just renormalize my matrix properly. So now the proper normalization is NPN, just because now the norm of each row is of order NPN on average of the square. Okay, so yeah, so this is perturbation. So this guy is zeroing out entries in Wn, and we ask the same questions. So what happens to the limiting distribution, and what happens to the extreme eigenvalues? So it turns out that if NPN goes to infinity, then the same phenomena on the macroscopic level happens. So the limiting distribution is still the semicircular law. However, for the extreme eigenvalues, this is not as clear. And that's what will be our subject. What about outliers? So okay, so what is known? So first, if NPN over log n goes to infinity, then there are no outliers. So I'm going to say a little bit more why. So there are no outliers. And this is due to, to many people basically. So first for Komlosh in 81, Wu in 2007, Benaish, George Bordenave, and Knowles in 2017, and Latawa, Van Handel, and myself in the same year. Yeah, I mean, so each was covering some range, some speed of convergence of NPN over log n. So Furedi and Komlosh was NPN bigger than log to the power 8, then log to the power 4, and then the optimal order in the last two. And if NPN over log n goes to 0, then you start having outliers, and so the norm of W tilde n gets away from -2 to. So why is this log n? So as we will see later, so this is the threshold of connectivity. And I mean, we can see it also in terms of, for us, in terms of concentration, if you want. So just remember that if you pick a row in your matrix W tilde n, and you calculate the expectation of the Euclidean norm squared, this is equal to, so in our case, it's equal to 1, because I normalized this. Now, I mean, our random variables here are just independent. Yeah, I haven't said this. Yeah, let me just take psi to be bounded in this case. So I have a sequence of independent bounded random variables. I can use concentration. So if you want Hofding, concentration tells me that each row is very well concentrated around its expectation. Each row well concentrated. Now, if you want all rows to be concentrated, then you will have to do a union bound. And that's where you need NPN to be bigger than log n. So if NPN much larger than log n, then you can do a union bound, and this tells you that all rows are well concentrated. So if you want, this dichotomy here that I drew above, if you want, we can write it in one, that in one, actually, you have concentration. So all rows are, the matrix is kind of well balanced because all rows are of the same norm, kind of. So concentration holds. And this basically will give that there are no outliers. And in two, concentration dramatically fails. So what I mean by it dramatically fails, it means that there will be a row which is much larger than the others. I cannot ensure that all rows are well concentrated. And then you can just see that the norm of W tilde n, which is, I mean, deterministically, it's bigger than the maximum Euclidean norm of a row. And since concentration broke down, this guy here, the maximum Euclidean norm, is much bigger. I mean, it will pump above the average norm, which we said it's a constant. It's equal to 1 here. So that's why, I mean, in this regime, concentration really breaks down the thing, just because the maximum Euclidean norm of the row may jump up above very much above the average. So what we're going to ask is there a phase transition like in BPP? I mean, we see that there are two different regimes here where two different phenomena are happening. And we can ask, I mean, what's happening around log n? Is there some phase transition happening at some sharp place around log n? So is there a phase transition like in BPP? And I mean, if so, what is this threshold? So this is basically what we studied with Kostya. So let me state the theorem.
Here.
Oh,
hey, sorry. I'm missing something. So in one, you say concentration holds implies no outliers. Is there a net argument somewhere in the middle, or? I mean, I thought you said concentration holds only in the sense that the maximum of the rows is bounded by 1.
Yes.
Right? So what's this implication? What does it hide? I mean,
it hides a lot of things. I'm just cheating here, completely cheating. I'm just saying that.
Okay. So it's just ideologically, it should imply no outliers, but you
yeah.
Okay.
No, it's not direct at all.
Yeah, of course. But is it like still some kind of union bound with the net argument, or it's much more involved than that?
It's more involved because, I mean, net argument, we're never able to capture right constant.
Yeah. Okay. So, so it just really suggests, but you need to do much more.
Exactly.
Okay, yes. Got it. Thanks.
So this theorem, which we proved, is the following. So what we were able is to completely characterize the norm. So let me just set theta n to be square root of the maximum between 1 and the gap between the maximum Euclidean norm of the rows and 1. So remember, 1 is the average. So I'm taking the maximum between the gap of the maximum Euclidean norm to the average and 1. Then what we showed is that if you look at the norm of W tilde n, it's actually equivalent to theta n plus 1 over theta. Okay, so what does it mean? So let's see what does it mean. So if we look carefully, so remember our threshold is, I mean, the outliers, we start having them whenever the norm pumps up above 2. And we can check when this theta n is above 2. And we see that whenever the maximal Euclidean norm of the rows is bigger than 2, then you start having outliers. This is again conceptual here, just because this is random quantity, but just by concentration, if you want, I can maybe here put lim_inf expectation. Then there are outliers, and the outliers are given by exactly this this function that I wrote here. So and equal to theta n plus 1 over theta n. And otherwise, there are no outliers. Now, how can we like link this to the BBP phase transition? Unfortunately, we cannot link it rigorously. So what I will do is I will just conceptually link the two. So there is actually a conceptual similarity with BBP. So let me tell you how we're going to see this. So if you, which is not completely true, but if you believe that whenever the rows are completely concentrated, then the matrix is very well balanced, then you don't have outliers, then you should see our sparsification as a perturbation which breaks down this concentration, and this is what is causing the appearance of outliers. So now let's just for the conceptual explanation, let us just suppose that only the concentration broke down a little bit and only one row pumped up above the others. All others are well concentrated and just one, which is, not the case, but let's just say that is the case. So say only row 1 became large. Okay. So if row 1 became large, so I meant that the row 1 of W tilde n became much larger than the others, than the average norm, which is equal to 1 here, but it's what I want is that it's equal to all others. So all others are concentrated. Again, this is just, just for conceptual illustration. So what we're going to do is that we're going to decompose W tilde n. We're going to see W tilde n as being some matrix Hn, which is well balanced, and some rank 1 perturbation. So how I'm going to obtain this decomposition here? What I'm going to do, all rows of W tilde n are well concentrated except the first one. So what I'm going to do is that I'm going to keep all rows of W tilde n unchanged, the same for I2 to n. What I'm going to do is I'm just going to change the first row. It's the first row which pumped up above the average. So what I'm going to do is I'm going to shrink it down. I'm going to remove from it the excess norm to make it around the average. So reduce. There are many ways to do that. Just you can imagine that you're just multiplying by the indicator that the norm is smaller than the average or whatever, something like that. So reduce the norm of row 1 so that it is around average. So if you reduced it to become around average, so what is left? You put it in the rank 1 perturbation X. Okay. So remember, when you're adding the X transpose, it's a rank 1 matrix because you're only changing row 1 and column 1, and all others you're keeping them the same. So what is left put it in X. So what is left basically, if we check carefully what is left. So if I had to reduce the Euclidean norm of row 1 to be around the average, so what is left, what I should put in X, is basically the gap to the average. So basically the magnitude of X is basically the gap between row 1 and the average. And the average, remember, it's 1. Okay. So now with this, with this decomposition, what you can just now say is that if the magnitude of X, so if row 1 is -1 is smaller than 1, no outliers. So this is the BBP transition. And if this is bigger than 1, then there are outliers. And we know what they are. And they are, it is equal to norm of X plus 1 over, which is exactly what we were saying in this here. Okay. So now this is completely conceptual because it's not rigorous at all. It's not clear how we're gonna reduce the norm of the first row. First, I'm also supposing that there is only one row. The statistics are much more involved than that. But I think it would be good, and I believe it may be possible to be able to link the two more rigorously by doing sort of decomposition. There were some results of Levina Vershinin and Rebrova, where they were basically doing a sort of regularization on graphs or on matrices to basically recover the concentration. And it may be a procedure like this to decompose the matrix W tilde n into some part which is regularized, for which we don't have outliers, and the part which is some finite rank deformation, which would really satisfy exactly the BBP phase transition. But still, I think it's kind of amusing that these two. There is this conceptual link between these two. And maybe one more thing is that it would be actually also interesting to understand. At least I don't see exactly how to interpret this in terms of a signal and noise model. So it would be nice to have this. So maybe one way to see it is that we have a signal which is completely lost in the noise, and we would like to ask how much should we clean it in order to see something, and cleaning it by zeroing out something. And this theorem tells us how much at least we should clean it in order to start seeing something meaningful. But it's not clear. Another consequence of the theorem. So what the theorem implies, the theorem is basically trying to compare for us the norm of a random matrix with the maximal Euclidean norm of its rows. And if you check carefully what it says that, so let's say for any epsilon, the norm of our matrix is smaller than 2 plus epsilon times the maximal Euclidean norm of the rows, just by analyzing this function, theta n plus 1 over theta. So with high probability. Now, of course, we always have the reverse inequality. So we always have that the operator norm is bigger than the maximum Euclidean norm of the rows. And here we're saying the opposite to that. So this is really, just so kind of surprising and so particular to random matrices. We're saying that this is the supremum over the whole sphere of the action of our matrix. And here, this is just the maximum over the canonical basis of the action of our matrix. And we're saying here is that it's the same, which is completely wrong in general, right? And just for random matrices, this seems to be a general phenomena. And actually, so this phenomena that the norm of the operator norm of a matrix is governed up to a constant by the maximal Euclidean norm of a row. This was observed. So this is this phenomena holds for all IID matrices. So matrices which have IID entries, this is true for them. This is due to Wigner in 2000. Now, what our consequence tells us is that we can capture the right constant 2 here, while Wigner had just some constant. Let's see. I mean, plus we also have some assumption, but at least in this case, we can recover the constant 2. And now, I mean, this phenomenon holds beyond the IID case. It actually holds for non-homogeneous Gaussian matrices. And this is due to Natawa, Van Handel, and myself. Okay, so yeah, I'm running out of time. So okay, so what? Okay, let me in the remaining time tell you a little bit about one particular model which is kind of interesting, which is when we are talking about random graphs. So for random graphs, it's still a little bit different, just because we will need to consider non-centered matrices. So more precisely, I'm gonna just restrict myself to Erdos-Renyi graphs. So we've seen this in Kostya's talk yesterday. So I'm gonna give you, I have a graph, GNP. It's a Erdos-Renyi graph. So you just every 2 vertices are connected independently with priority Pn. So I'm gonna denote An the adjacency matrix. So you just put 1 or 0 depending if you have an edge or not. So in this case, it's just a Bernoulli matrix. And just notice that the average degree in the graph is just equal to NPN. Each vertex has on average NPN neighbors. And you ask the same sort of questions, just because spectral properties of this adjacency matrix, they imply some expansion properties of the Erdos-Renyi graph. And it turns out that as long, again, as NPN goes to infinity, if you look at the adjacency matrix properly normalized of this Erdos-Renyi graph, then this converges again to the semicircular rule. And what you're gonna ask, what happens to the other eigenvalues? So now remember here, the model is not centered. So I may have that the largest eigenvalue is doing whatever it wants, just because the centering cost me some rank 1 matrix. So here, the expectation of An is just Pn times 1 transposes. The matrix was all 1s and times Pn. So it's a rank 1 matrix. This one is already shifting my spectrum. And this, I mean, the largest eigenvalue was calculated by Krivulevich. And Sudakov, who basically showed that the largest eigenvalue of this adjacency matrix, it is of order the maximum between NPN and the maximal degree, square root of the maximal degree in the graph. So here again, so if you look at, so if NPN, if you want, is over log n is going to infinity here, then all degrees are very well concentrated in the graph. So the maximal degree is NPN. So this maximum here for lambda 1 is NPN. And this we can also see because when we have concentration of degrees, GNPN is kind of almost regular. It's almost an NPN regular graph. So maybe let me denote D is NPN. Almost D regular. Okay, so lambda 1, yeah, I'm running out of time. Lambda 1 of an is of order d. And what you ask is, what about lambda 2? So as we know, the bigger the gap between lambda 1 and lambda 2, so the bigger the spectral gap is, the better the expansion properties of our graph is. So what is the biggest gap possible between lambda 1 and lambda 2? It is when lambda 2 is stick to the bulk of the spectrum. So it is when lambda 2 is around 2, basically, 2 square root of. So so if you want, we are asking when is GNPN a kind of, optimal spectral expander. By optimal, I mean is when the gap is the largest possible, which means when lambda 2 is stick to the bulk. And once again, we can, it's actually similar machinery, it's just a bit different in some technical aspect. But what we can show, and in this case, we can completely calculate this threshold because, the laws, we know it's by, we know the maximum of binomial distributions, so we can explicitly calculate these quantities. And what we find is the following. So if lim sup of NPN over log n is smaller than 1 over log 4 over e, then there is outlier. Then GNPN is not an optimal expander. Actually, we even know that lambda 1 and lambda 2, they will glue together asymptotically. And if lim NPN over log n bigger than 1 over log 4 over e, then it is. Okay. It is an optimal spectral expansion. So let me just end with 2 words. One which I should have mentioned before, that this result was obtained by Alt, Ducatis, and Knowles independently, and even the result previously, which applies also for Wigner matrices. And it's even more than this. So what these people are able to capture, it's more than what we did, in the sense that, yeah, maybe I should mention the second trimer first so that you understand. So what is this 1 over log 4 over e? It's not just some random number. It's actually the place, this is the threshold of emergence of vertices which have twice as much neighbors as the average. Yeah, I'm finishing. So threshold of emergence.
We cannot see the last line. So if you move up a bit.
Now?
Better.
Okay. So threshold of emergence of vertices with twice as many neighbors as the average. As average. So this threshold is complete. It completely characterizes the thing. So what Alt, Ducatis, and Knowles observed is that it's not just this, is that every vertex which becomes a hub in this sense. So for every vertex which has twice as many neighbors as the average, each one of them result in a new outlier, in a new eigenvalue which pump up out of the bulk. So every vertex becoming a hub result in an outlier. Okay, so yeah, I don't have time to tell you about the proof. So it's some refined very much refined moment method to capture all of this. And the main idea is that this threshold, which is twice as many neighbors as average, you can just see who's the one contributing for this, and these are the three which are rooted at vertices which have maximal degree. And the whole job is to show that this is the only example which matters among all possible things which bump up in the moment method. So I'll stop here. Thank you. I'm out of time, right?
Basically, yes. Yeah.
Okay, yeah, so I'll stop here.